Hello.
Sure. So I looked over the exam, and I usually tell my students in all my classes, online and not online, that I don't appreciate the approximation problems. That's the linear approximation and stuff. I don't put it on the test. Students tend not to do well with linear approximation, so I don't like it. Approximation. It's nice homework problems, and you will see them later in physics and engineering. In computer science, actually use it a lot. They just call it differently, and they look at approximation methods and stuff. Euler's method and others. We're gonna have more approximation methods in calculus 2 and calculus 3. But for the test, it's just students tend not to do well on these. That's why I took them out. No Rolle's theorem, if you remember that. Last time I mentioned that too. So you can skip that too. Everything else, let's review. So I have a list. In my list is going from these exam reviews because that's the legal stuff I can show. Be very restricted on things I can show. And I know that I can show stuff from the exam reviews. So here they are, 4, 5, all 5. And I'll be going through these. And they're all in modules, just reminding you. All of this is in modules. And I will be numbering them for you in case you want to see. So I start with limits. Let's go back to limits. To be honest, yeah, because final exam has limits, several problems, limits. That means I will start with exam 1 review. And then I will do number 8. And there's so many things I want to show. Exam 3. Well, actually, I can check that here. I think it was number 8. Oh yeah, of course the graphs and everything. Yes, let's do number 9. I said it says or. That was curious about it. Let's do number 9. And other stuff you need to know. You need to know these classical 4 cases, which in front of you. Yeah, 4 cases. Fraction on top of the fraction, square minus square, factoring. Well, we don't expect you to remember cube though. X cubed minus 1000. But definitely multiply by the conjugate. So let's do 3. We're done with 3. That is number 9. Limit x approaches, I think, 3. Just not to mess up like that. Exam 1. Oh, it's a wrong class. That's why everything looks so different. I opened the 66 on my computer. So you write down the limit I just showed you. It is, and we have to go through the graphs for sure. That's actually, I think, the most important. Limit as h, let's put h, fine. H goes to 0, 3a plus h squared minus 3a squared over h. So I will be going fast as always, and then you stop me or put in the chat what you feel you should ask about. Because it's a review, so I want to go fast to cover more. I think that's better. So in this case, we can expect you to know the formulas for this whole limit section. It's called algebraically. Algebraically. We expect you to know the formulas. We expect you to know x plus or minus y squared. It's a square of some or different. Plus or minus double product y squared. We expect you to know x squared minus y squared equals x minus y, x plus y. Those two are the most important. Multiply by the conjugate if you need that. That means multiply by the square root, another sign, square root, and then it all goes to the second form. In this case, we're just going to do 3a squared plus 2ah plus h squared minus 3a squared. The goal is to get rid of the bad guy. And in this case, h equals 0 is the bad guy. So I hope by simplifying a lot, the bad guy will get canceled out. 3a squared plus 6ah plus 3h squared minus 3a squared divided by h. Something should go away because then I can factor out h and the bad guy goes away. The division by 0 goes away. So, of course, equals limit h got factored 6a plus 3h over h goes to 0, cancels out. 6a plus h goes to 0. 3 times 0. The answer is 6a. So you remember this from the first exam. We expect you to remember it again for the final exam. And ironically, you will not be working with limits forever, actually, after that. Vectors will have some limits and calculus. To be honest, like this. The idea is important, but all those algebraic stuff is boring and kind of, yeah. So practice number 8, number 11. In exam review 1. If you just joined, then I'm just reminding you I'm working on exam 1. So factoring, sometimes you need to factor by yourself. There was like a problem where you need to know how to factor these problems. Or like you need to expect to create it like squared and stuff. I know the students are slow with this, so I deleted these problems and changed to those who already have a factored form. But in general, remember, you need to know correct formula and how to do nice factoring of that. Good. Now, number 15, it says here. Let me see what's number 15. Nope. Oh, yeah, this. So let's do this one. Let me do snip. How to work with piecewise functions. Good. And also this example is nice because it reviews lots of definition. Piecewise functions and the function that's made of pieces. That's actually your bills for electricity. This month I paid $200, but last month it was $250, and before that it was almost $300 in Arizona for AC. And that's not continuous at all. So it has like big jumps actually. That's called piecewise function made out of pieces. So here it is. Here's the function 4x minus 4 and 3 over x plus 9. Before 8 and after 8. And they ask you limits. What is happening right before 8? What is happening right after 8? And what is happening at 8? From this answer, the answer about continuity follows. Is it continuous or not? Why? Let's remember what continuity is. Continuous functions require this one very beautiful, elegant formula. The limit should exist. Limit of what? X approaches a. So in this case, it's 8. But then if it just exists, there still might be hole. To make sure that there's no hole, this should be matched with f of a, this guy. So when x approaches 8, in general, f of 8 also should be the same number. So put this in the box. This formula means left limit should be equal to right limit in order for the left-hand side to exist. So limit x approaches a from the left should match with limit x approaches a from the right, like so. That is in order for the left-hand side to exist. But still, all of this have to match with f of a. So let's figure it out. This is when students get lost. So sometimes I like visualization. So I like to draw this line, and I can see something happens in 8. So I will call this function number 1 and function number 2. You don't have to learn it this way. It's just my way of explaining it. And I see students like it. So on the left from A, literally on the left over here, function number 1 happens. On the right, function number 2, and at a, because of this equal sign, 2 happens. And now I know where, and now I know when to look where. So when x approaches 8 from the left, negative sign means from the left. Remember English, so it's from the left, not to the left. From the left also means x is less than 8. So first of all, I already know to look here because x is less than 8. But what if you don't remember that? What if you don't remember that from the left means less than 8? Then visualize. How does my pencil approach 8 from the left? Like so. What function am I covering? Function number 1. So I need to look at number 1. That means I'm looking at limit as x approaches 8 from the left. Let me put it so. Equal sign of 4x minus 4. And now you minus that 8 minus. You forget about from the left part, and you just plug this number into the function you chose, and you get 8 times 4. Maybe should write down 8 times 4 minus 4. What is that? 32 minus 4, 28. Now let's see what's happening from the right. And the same idea happens from the right. X is bigger than 8, or from the right. We need to use function number 2. And I'll skip explanation. I'm just going to plug 3 over x plus 8. No, 3 over 8 plus 9. So I'm plugging 8 everywhere. And I kind of ditching the plus sign over there. The plus sign only tells me the direction we're moving, from the left or from the right. So after this, when you plug numbers, doesn't matter anymore. That is obviously not 28. So there will be no limit. 3 over 17. So not only immediately, the limit does not exist. Left limit. Left limit. Left limit is limit from the left. Does not equal to right limit. Thus, limit as x approaches to 8, f of x does not exist. D and E. And actually, that immediately gives me a jump as the answer. It means left limit and right limit, they separately exist, but they do not meet each other. So the function jump actually literally from height 28 down to height 317. What is f of 8? You need to look at where the equal sign is. You find, locate, identify equal sign, and then plug your 8 into that function. 3 over 17 again, because I'm using function number, let me put it in green. Function number 1, function number 2, function number 2. Like so. So that means from the right, the hole is filled, actually, but it did not meet whatever is from the left. Check the check. Okay, good. So you need to be good at this. Kind of, that's a good stuff to be, it's kind of important stuff to be good at. Lots of applications and so on. 15. What else? This was 1.5. 2.5. That's fast. Okay. Let me see, what did I write down for 2.5? 1.6. Oh yeah, these ones. Did I write it down? Oh, I just assume I will remember. Okay, let's just do that. Then 1 goes up until 2.4, I think. Find equation of the line. Yeah, I will do the tangent line in a second. Yeah, up to 2.3. So let's work on these infinities. Also, I hope you remember infinities. Those are very good problems if you know how to do them. So that's the problem. You need to know how to do them. It's kind of like if you do know, you're happy about it. If you don't, that's the struggle. So let me probably change some of them. Let me check this one. And a little bit more on that. So those chapters were called 1.6. And those are infinite limits and limits at infinity, whatever, that's the English for you. Basically, a limit that involve infinity, either as an inter or as an input. So let's do that. These guys, I gave you nice shortcuts how to be fast with these. In my videos, also explain how I teach in class. So they tell you to like divide by the leading coefficient with the highest power, blah, blah, blah. I don't do any of this. I find the leader of each side. The leader of the bottom is 9x. Plus 6 is a constant. 9x at infinity, it only works at infinity though. At infinity, 9x is the leader. Plus 6 is like a tail of the comet. It will follow 9x. Plus 6 at infinity is still 6, but 9x at infinity is billions and billions and so on. So find the leader here and find the leader of the top. Leader of the top is 5x squared, but it's inside of the square root, so it's actually square root of 5x squared. In class, I should go to the projector and I close my hand, the constant. And then it is legal to write down that the original limit matches, or the answer for the original limit will be the same as this limit, where I'm only taking out the leaders. So, and then you just calculate, it's going to be simplify square root of 5x over 9x. Guess what? They simplify. Limit x goes to infinity. Go away, square root of 5 over 9. So in general, I teach this idea. If the top wins, that is example. So at infinity, let me do that. At infinity, you find the leader of the top and define a leader of the bottom. If the top wins, example, limit of x to the 5 minus 3x over x cubed plus 10, right? X goes to infinity. Top wins, it gives you infinity. It can be plus minus infinity and also can be D and E if left limit is not equal to the right limit. But at least you know it blows up because infinity over stuff is infinity. And if top wins, it means infinity, the top increases faster than the bottom. And at some point, the difference will be so big that everything blows up. Now, if the bottom wins, it's like I'm imagining it as competition of two universes. One is expanding to infinity, and another one is expanding to infinity. Then we're finding ratio. Which one wins? Sometimes they have the same speed up to a constant. That means x cancel out with x. They have the same speed of increase up to a rate. And that's why the rate is the answer. But then if the top wins, everything goes up. And if the bottom wins, everything shrinks to 0. Because x7 minus 3x. If you divide by the biggest numbers, you know, you get the smallest number. You know, that's like number sense for you. So you compare the leaders. And you get the answer. Finally, same powers. And by powers, it's actually kind of a fun pun. Then we're talking about superpowers of expanding universes and so on. But exponents, right? They have the same exponents. Then no matter what is happening after those leaders, 7x to third minus 7x squared plus million or whatever that number is, doesn't matter anymore. X cubed, let's do 8. 8x cubed plus x squared minus 10 minus 100x plus pi. Again, they follow the leader. It doesn't matter at infinity what's the tails are. They cannot compete with the leader. So you just find the leader. If the speeds are the same, the answer will be 1. But since each of them have some kind of rate in front of them, then the ratio will be the ratio of those leading coefficients, like so. So here are your 3 examples. Top wins, bottom wins, same powers. At infinity, of course. That is my review. So review these limits. There are more like this in your homework. And these guys, you see, minus infinity. Here is like this guy over here. Find the leader of the top of 2x squared plus 2x. The leader is 2x squared divided by minus 5x squared plus 7,500. Okay, I found two leaders. 2x squared over minus 5x squared at minus infinity. Well, they're the same, so the answer will be 2/5. 2/5. Because minus infinity squared is plus infinity, and minus infinity squared is plus infinity, the answer is positive. But if it was cubed, for example, that could mess up the sign. Not in this case, but it could. And you saw it in your homework before. So this is how fast you can do this problem, including this problem here. See, I put this problem on the test for my in-person class, and students did really good. Because I told them, don't be afraid of occasional problems. If they say in a long run, that's, for example, in a long run, how fast the medication will dissolve in your blood after the injection. Well, apparently it sometimes takes 6 hours, sometimes 36. That's in the long run. At t, it goes to infinity. Find the leader. The answer is 44 over 11. Boom, done. So don't be scared of these guys. Infinity squared minus squared. If you see squared, you know what to do. Multiply by the conjugate, which I can actually show you. Multiply and divide by the square root plus square root in this case. So when you change the sign, this part over here becomes a minus b times a plus b. And that gives you a squared minus b squared. A squared gives you x squared plus 10. Minus b squared gives you x squared minus 10. And then unfortunately, you still have this ugly square root plus square root. But square root plus square root will not be 0 anymore in these cases because we're adding 10 and stuff. So we're not going to divide by 0. And so it doesn't make the whole fraction a bad fraction. But the good part, this guy got eliminated. So you will have 20 over square root plus a square root. This is the time when you actually write down what is in those square roots. X squared plus 10, x squared minus 10. 20 over infinity. Infinity is the biggest number you know. You're dividing by the biggest number you know, it goes to 0. But it only works when x is infinity though. So those tricks do not work at 5 or 0, x goes to 0 and stuff like that. Plus minus infinity. So yeah, this was good too. Make sure you review this. I think there are only 2 or 3 problems with limits there, so it's not too bad. Oh, there's no definition of derivatives. Truth is. Are you kidding me? I should have read them. Yeah, I only they put it once. I never liked it even one time. But I always tell students it's so unnecessary, long, that no definition of the derivative. Derivative by definition. So yeah, don't expect that. Now, so you can keep that in your review. What else was on my list? Let me check. I think I moved to exam 2 after that. Definition, we don't need that. Continuity, we just checked briefly. And of course, product rule, quotient rule, chain rule. That is already on the next exam. So let's go to the exam 2. Exam 2 has lots of things. I remember you did not do well on exam 2, but don't be scared. I tried to put there the stuff you know. So hopefully that helps. Right, let's see. We're starting with 2.4. I have 2.5 in my notes. So let's have 2.5. 2.5, let's review number 7, 8, those kind of things. Oh, number 7, I can actually just, oh, how convenient. They have a solution right in front of you, kind of spoiling the fun, but it's fine. Let me show you. We worked on that. Limits of infinity. Let me put this in the table. And now it's going to be exam 2. Exam 2, lots of differentiation stuff. So make sure you know everything. Like let's see, basically master exam. And by everything, I mean product rule. Well, of course, power rule. We don't even list it because that's how basic it is. Power rule, quotient rule. And then we have the least favorite of everyone's is chain rule. That makes it objectively makes everything complicated, functions and the function. Then we jumped into logs and exps at some point. And then you're supposed to know how to do all the previous stuff with logs and exps. Then we jumped to TRIGS. And then just recently you had inverse TRIGS. Inverse TRIGS. I'll help you right now to memorize inverse TRIGS. I think those are the hard ones for people. Now, implicit differentiation. Logarithmic differentiation. So those are your skills to differentiate things. I have to tell you, it's important. You will not be able to survive calculus 2 or 3 if you don't know how to do all of these things. There's so many trigs in calc 2 and calc 3, and we're working with derivatives in integrals. They're so fast that you need to be good at that, at this stuff first. So exam 2 review, I'm using that one, and I found this tangent to the 4. Exam 2 review, number 7, as you can see. Y prime equals. So what I see is that we have tangent x, and everything is to the 4. So first I see that the stuff inside is some kind of function. Let's call it u. I know how to work with u to the 4. I will not circle it. I will actually put prime. U to the 4 is 4u cubed. Okay, so I can do that. I write down 4u cubed, but then u was substitution, so why not to put it back right away? Because you have to answer in terms of x anyway, so just put it back. So 4 goes down, copy the function, copy, so derivative at the original function, change the power, and now you do times, and that's when the chain rule happens. Chain rule says, please don't stop, there's a chain reaction that's happening. Differentiate the function inside as much as needed. So maybe there's something inside of tangent. And inside is going to be derivative of tangent is secant squared x. And that is the end. So you basically, should I review formulas? Let me review after those examples. For now, just practice the chain rule. So you need to know that and how to work with chain rule. The other one, you see the same thing with cosine cube. Nothing really different. 3 goes down, cosine squared times minus sine. Boom, type it and you're fine. And then if they ask you to find equation of tangent line, you proceed. Do I put it in my list? I decided to do a different problem with the equation of a tangent line. Let me see. This is number 15. There's some problems that combine all of this, a little bit of everything. Let's see. This table, I did not put it in the test. People don't do well on it. I tried once. I mean, the department gave it to us. We put it on test and then nobody did well. So yeah, no, thank you. Okay, let's do this. This problem reminds you many things. Product rule, implicit differentiation, and equation of a tangent line. 3 topics at once, and that's why I chose it. That's 2.6. 2.6 copied. 2.6, if you remember, was implicit differentiation, your favorite topic. Surprisingly, again, implicit differentiation is so important in applications. Most of the time, functions are not beautiful. It's not like, oh, a colleague of my lab Can you tell me what do we have as a model for the rocket going? And you're like, oh, the model is f of x equals blah, blah, blah. No, it's never like that. It's always like this. It's a math. It's a math, and now it will be involving derivatives at some point, dy and so on. And that's called differential equation and more. So applications don't have beautiful things in them. And that's why you need to know how to work with the math. So beautiful things was the basic. You learn the basic, now they tell you the truth. Nothing is so simple, and then basically that's how it is. So that is implicit differentiation plus product rule, plus tangent line, equation of a tangent line. Let's review all three topics at once. That's why I like this problem. Number 15. Step 1. If you see that you need to do implicit differentiation, and why do you need to do it? Because there's no such a thing as y equals blah, blah, blah in order to take derivative. So you just drop the poem of differentiation, differentiate everything. So I'm going to take derivative of the left-hand side and right-hand side. In the left-hand side, I see product rule. And let's divide it in like these pieces. You could actually do 5 outside and then x times y and so on. But it's fine. Product rule. Let me zoom in. Derivative of 5x, and that's just 5. Copy v, y to the 5, plus copy u, that's 5x. Derivative of y to the 5, 5y to the 4, and you would like to stop, but don't, times y prime. Or if you want to be more professional, then dy dx. In the related rate, that matters because the third variable shows up. So every time you differentiate something with y prime shows up. Or you see it this way, it is chain rule. Let me explain to you what. Again, chain rule. So x is my input. It's also called independent variable, right? So derivative of x is 1. Derivative of 5x is 5. Nice. It's actually 5 times 1 if you think about it. But y depends on x. So there's something inside of y. Thus, derivative of y is 1 times y prime. Because it will be 1 times by the chain rule. So it's still chain rule. Derivative of the function inside, but we don't know what y prime is. So we're going to just keep it as y prime. And you can say 5y prime will be 5 times 1 times y prime. That's the difference. Yeah. Continue. That was just product rule. So I would put like a brackets. I like visually see the different pieces. Plus, one more product rule, right? So let's do that. Let's isolate it like so. U and v. So derivative of 3x is 3. Copy y plus copy 3x. Derivative of y is 1 times y prime. Like so. Let me put it in this color. And now I like to use make a mistake on purpose. The answer is 24, but remember derivative of 24 is 0. So people get happy that they're done, and they forget to differentiate the right hand side. Now, your goal, step 2. Step 2 is implicit differentiation. I determine pieces with y prime and move them to the left. Everything else, I push them to another side, to the right. You can mix up the sides, doesn't matter for me. Some people do it exactly the opposite. So I'm gonna move everything with y prime to the left. In this case, it's already on the left, and I can already start simplifying. 5 times 5 is 25. Next, y to the 4, dy dx, plus 3x, dy dx equals. And now there, other things is garbage. Just move it to the right. We don't need it to the very last step. Minus 5y to the 5 minus 3y. Let me see if you have questions on this. Now you can actually start writing down the answer if you visually can see it. But I like to explain it with more 2 steps. Step 3, factor out whatever you're trying to find. The whole goal is to have blah, 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 blah. divide dx equals blah, 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 blah. But to have that, you need to have right-hand side over the factored part. So I'm going to put in brackets. The part I'm going to factor is going to be 25xy to the 4 plus 3x. And don't write down the right-hand side. It's the same. You can copy. RHS is right-hand side. The answer follows right now. Divide x equals right-hand side over the factored part. So some students figure out how to write it down right away. Minus 5y to the 5 minus 3y over 25x y 4 plus 3x. That is the answer if they ask you to find y prime derivative of y using implicit differentiation. That's the answer. But this problem has more steps. So let me color code it. This was implicit this part, step 1, 2, 3, 4 was implicit differentiation. Why are we doing this? They ask us to find the slope of the tension line. Oh, let's find the equation of the tension line. So I can review formula. Equation. EQN means equation. Equation of a tangent line. Well, equation of a tangent line has steps. So now I'm going to do that. Equation of the tangent line. Step 1, find y prime. Well, we did that. That just took forever, but we succeeded. So, yay. That's what we just did. You can copy it here. And actually, that's the case. Like the first step is the hardest. Sometimes people do numerical. If you remember linear approximation and other things, they do that for the first step. Now in calculus 3, you're going to do 3D and more steps to do the first step only. Find slope. Slope is not y prime. Slope is y prime with a point. So slope is y prime at whatever x they gave me. And they gave me likely both x and y, 3 and 1, because they knew that, well, actually, it's fine. Let's have it like this. Because they knew that using implicit differentiation, x sub 0, y sub 0, the answer for y prime will include both x and y. Okay, take a pencil. This is where people tend to mess up. So I highly recommend take a pencil and sign what are you plugging instead of relying on your brain. I hope it doesn't sound offensive, but I always sign everything. Why? Because when you sign it, first all the y's are 1s, and then you sign all the x are 3. Now you're not gonna mess up. But somehow I see it all over again on the test that people tend to mess up when they plug it in. And it isn't gonna be upsetting to mess up at the very end. So it's gonna be minus 5 times 1 to the 5, minus 3 times 1, 25 times 3 times 1, plus 3 times 3. Good. Yeah, this is some kind of number. Actually, don't they give me the answer here? The answer is minus 2 or 21. It's minus 2. Is it? Then I mess up a sign. Was it plus? Maybe it's a typo. Find the slope because they gave me the slope. I have minus 8. Oh, maybe it's simplified. Minus 8 over 75 plus 9. Yeah, they probably just simplified. That is 84. Okay, minus 2 divided by 4. 21. Nice. That's my slope. That's called M. Do you know that nobody knows why the people start calling slope M? There's a Wikipedia page saying about it, but actually there's no record who started it and what. Step 3 is almost the end. You need to know so find y sub 0 if needed. If we did not give it, then you have to find it. But luckily, it was given. Y sub 0 is 1. Do you know how to find it? Plug into, no, plug what? Plug x sub 0, 3 into original. Like so. And then 1 will pop out. So this next step is basically the end. Step 4, you need to know the formula y minus y sub 0 equals mx minus x sub 0. That's the slope point intersection formula. Or the other one, if you look at y equals mx plus b, find b, and so on. I use this one because I like that everything can be plugged in right now. So x sub 0 was given. Y sub 0 is 1. M we found minus 2 over 21. Step 4 is the answer. Step 5. You nicely rewrite it. Y equals 1. Many people just move it right away, but then I see that they lose the sign if there is a negative sign. Minus 2 over 21, x minus 3. Simplified. Minus 2 over 21, x. There are some fractions. Plus 6 over 21 plus 1. Yes. 21 is 21 plus 21. So the answer will be plus 27 over 21. Oh, no. So we reviewed 3 topics. Equation for tangent line, and then also implicit differentiation with involved product rule. Right. That's what I want to show. What do you think about that? Now, related rates. Related rates, I did not put anything hard in related rates. So don't worry about the long problems. Whatever is long, this woman walking, yes, kidding me, the similar triangles. Who has time? Listen to test. No similar triangles. Either is these obvious ones, or I like balloons and circles, like people usually know that stuff. So let's do the balloon one. Both cases. So I will show you how to deal with, well, I guess I should actually. How to deal with first both cases. Oh, I have a note. Related rates, of course, is like the least favorite topic because technically for me, because of English, I don't like reading in my math class. That's why I'm taking English class. Good enough. English and biology classes and history classes have very enough English reading. But in American system of education, they argue that we're not supposed to give people pure mathematical concepts which they have no idea how to apply, blah, blah, blah. So you want it to be more interesting? Here you go. I'm pretty sure that the generation of your grandparents were complaining related to that it was too boring and who needs that and blah, blah, blah. Well, now here you go. I seriously think so. That these grandparents grew up and became in charge of educational system at some point, right? They are the policy makers. And now we have all of these problems. This is what you deal with. I don't know, there's pros and cons for that. So step 1, read the problem, make a picture. Okay, it's a spherical balloon. I don't even read after this right away. I know it's gonna be a sphere. So here you go. I'm writing down, I'm drawing the sphere. They say that the radius is increasing. What? That means R over with respect to T is changing. Well, it says per minute. That's how I know it's T, not some kind of other stuff. We did not do problems with other stuff yet, but it's actually increasing with respect to surface area too. So there's lots of relationship, you know. Anyway, when I see the keywords per, that I know it's derivative, but in general I see increasing, decreasing, or changing. Changing is derivative. Rate. It actually says to you it's rate. Rate of what? Of radius. Oh, so that's the R over the T. Write down right away what you have. The R over the T is 2. Nice. How fast? Oh, so they want me to find another rate. Well, that's what it's called the rates. Duh. How fast is the volume changing? You see keywords? Volume changing. So now I can write down. They want me to find dV over dt equals question mark. When the radius is 12, no per, no changing, no words about rate. So that means R is just 12. R is just 12. Here's R. Picture was useless in this case. Not useless. Thing is to know the formula of the volume, basically. Which is what? 4/3 IR cube, right? What was it for one? Who remembers? Let me put this in the box first. Who remembers? First of all, I want to say this guy, plug it in, plug later. Let's see, later. If you plug R too early, then the derivative will be 0. So that's what some students get confused about that. But you first take derivative and then you plug. That's kind of not obvious, I guess, but when you try it, it makes sense. It's something that's way too easy. So you need to create a relationship. Step 1, write down everything is given, what is given, what is not. Step 2, write down the formula. Everything you know, formula. In this case, they're talking about volume. What? Volume of the sphere. So I'm gonna write down volume of the sphere. Is it 4/3 or 3/4? Pi R cube.
It's 4/3. So when you do the differentiation, the bottom 3 goes away.
Oh yeah, nice, nicely canceled. Oh, thank you. So you put this formula. Actually, I don't remember if we gave you formulas or not. I hope they did. I copied it from your homework, but just in case, probably memorized. So we do expect you to know basic formulas for the area of the disk. What a disk. Disk is a circle with stuff inside. So it's filled circle. That's what they call in English disk. Pi r squared. Remember, squared means second dimension. Second dimension, it's area. Cube means third dimension. That's volume. And then guess what is 2 pi r? 2 pi r is circumference, right? So that's how you know it's keep increasing the dimension. Line versus area versus volume. So that's how you can try to remember. And just like you just said, also convenient to remember that 3 will cancel out 3. That's how you know it's 4/3. Okay, so I have this. They asked me to find the VDT. So to do that, I will just differentiate everything, keeping in mind that V depends on T and R depends on T. So it becomes a implicit differentiation where V is the function of R, of T, and R is the function of T. And they are related through T, through third dimension T. That's a three-dimensional problem. dV dt equals 4/3 times 3 times pi times r squared. Now, just like before, every time you deal with a variable that has another variable inside, you need to do times dr dt. Here you go. 2 related rates popped out. Everything now depends on you reading the problem, on you reading the problem. At this moment, I can ask you to find this guy, and then I give you dv dt, and you just solve. Just plug everything in, you're fine. R is still 12, so that's not a problem. Or like in this case, it's easy. In this case, I mean, it's just a little bit easy because it's left-hand side is the one that they wanted to find, while the R is given as 2. Plug everything in, get the answer. 4/3 and 3 cancels out. 4 pi 12 squared times 2. Literally type this in and you get the correct points for the web. In the solution, they give you approximate answer, 3619. Approximate, 3619. I don't like when they cut out pi. Pi is too sacred to cut it out, too important. So here you go, related rate. Review both cases. So find the R over dt if dv over dt equals 5,000. Now I just want you to practice that. How about that? And how would you write it down? How would you read it? Find how fast the radius is increasing if the volume is increasing 5,000 centimeters cube per minute. Also interesting, did you notice it is positive as it should, because the original function is increasing. And this one is positive as it should because the v is increasing. So it should make sense. Now, so in my in-person class, I gave people a problem about the oil leak, which is very cool because it's very practical. The oil leak happened in Florida, and then here it is. And now it's actually spread like a nice circle, basically a disk. So the scientists told us, it was like, what, 5 years ago, 10 years ago? They mentioned how soon the oil will reach the beach, and they started evacuating it. How did they know? Because they used related rate problem solutions. They knew the rate of one thing, and then they knew the water rate, how the water is spreading. So they could calculate how fast it will reach the shore, and they could evacuate people with respect to that. So pretty cool. Now, for you to know also, okay, like side topic, but concavity matters here too, because the water spread, the leak spread it fast at first. So the derivative was positive, and a big, positive and big means it's going fast. But then it starts slowing down. Like at some point, the leak slows down. Now it's barely changing. That means derivative is still positive, but small. That means concavity changed. The second derivative became negative. Concavity changes when something is keep increasing, for example, but slows down, or something is decreasing and then slows down or speeds up, and so on. That's a cool example, I think. Now, 2.6 minus 15 relates with this number 2. Let's see, what did I do? I did number 20, yeah, that's what I noticed. And then axis. We did that. Okay, 3.3 is it next chapter? Okay, linear approximation. Yeah, just ditch that. I don't like linear approximations. And differentials. So I took it out of the exam. See that. What is that? Limits at infinity again. Oh yeah. Sure, let's do this one. Limits at infinity. This one I can tell you fast how to do it. Let's copy both. 3.1. So we introduced logs and exps to you. That involved limits again. So back to limits. And the idea is exactly matches with what I'm teaching anyways. And that's why I like this idea. Don't have to be don't overthink this. Find the leader of the top. Your job and the bottom, right? Your job is to know who is the fastest one in the room. Polynomials have no comparison to exponentials. Exponentials functions are fast. They're actually not the fastest one. So in the speed world, log of x at plus infinity. Log of x is growing, but it is slow. Line x is growing, so it's linear, but it is slow. Polynomial, so say x to the n, growing faster than line. Okay, fine. Then we have e to the x, or exponential in general. So that's why in the movies they always say, oh, the epidemic spread exponential, and the audience know it means fast. But actually, there are two functions faster than that. And factorial. Factorial will show up in calculus 2. You've seen probably before or not, but it doesn't matter. Calculus 2, we're going to review it for you. It's actually faster than e to the x. But factorial doesn't happen in nature that often. It's everywhere in statistics. But in natural, e to the x shows up more. And the other function is x to the x. You probably have seen it when you were working with logarithmic differentiation. X to the x, or function to function, because it's like exponential and polynomial at the same time. That's the fastest. But in our classes, we usually don't go beyond these. Well, actually, when factorial is going to show up in calculus 2, you will remember my teaching, and you'll be like, oh, I think she mentioned it before. And you'll be doing exactly the same thing. If factorial is over here, it's going to be x factorial. Then that's it. It's infinity, because it wins. If factorial is over here, then denominator wins, and everything is 0. So the logic will be the same. In this case, find the leader of the top, leader of the bottom. Imagine the constants not help. Check the speeds. A to the x and a to the x have the same speed. They kind of literally cancel out in this case. So the answer will be 2 over square root of 11 over, not over, 2 times square root of 11 over 7. Same thing here. Okay, 5 to the x at infinity goes to plus infinity. And that's a mistake because then you see it's minus infinity. And as I told you, all of this is at infinity. At minus infinity, 5 to the x actually shrinks to 0. You need to remember either graph. On the right, exponential function goes crazy up, but on the left it shrinks to 0. Like it wants to hug the floor, but it never does. It has horizontal asymptote. Either remember that, or imagine it is 5 raised to the minus infinity, which is 1 over 5 to the infinity, and that is 0, right? Imagine that, because you can work with negative signs. That's the second way to do it. And the third way to do it is to take a calculator and actually check what is happening. Plug a huge but negative number, minus 100, and see what the calculator will gonna give you. Is it gonna give you like 5 billion? I mean, I'm not sure what's the number is gonna be. Say 1 billion, or it's gonna be 0.00001, right? So that's how you know. You can literally do it everywhere. You can plug it here. You can always check things numerically. Just plug everything in your calculator if you want. So you can always see what is happening at 1000 and see where it's going. In this case, it will be hard for you to know the answer, but at least you can see these little pieces and their behaviors. So the answer is 9 over 0 minus 7, which is 9 over 7. Okay. What do you think about this? Those are exps. Write down. Let me circle it. This is topic of exp and limits. So review that for sure. I mean, that is pretty important. Exps and logarithms. Okay, no, like these guys. I'm only gonna talk about, I never put in a test the derivative of inverse. I do the same thing in my in-person classes. People don't do well on this. They just never do. Let me also write it down. We used to do it. I mean, they always put it in the test. And I mentioned it for the exam 2 or 3, whatever. Yeah, we're not gonna do that. So no, we put it here. It's derivative of inverse. So just this formula, minus 1 prime is 1 over derivative of the original and inverse of A. Nobody can do it well. I mean, okay, I should not say that. It's amazing if you can, but from what I remember, it was a disaster. So, yeah. And also, it's objectively not an important formula. It's important to know it exists, and if you ever bump into it, you will search it in the book, which is called Google, and then you use it. But knowing it by heart is not important. I'm just letting you know as a math major. Yeah, no, that's not as important as these things. Everything here, what I just showed, is actually pretty important. Next. Limits. This one actually is a cute problem. I quickly gonna show you that. And it's in my list anyways. Let me show you this one. Now we introduce logs to you, and then we continue basically talking about limits, but with exps and log in this case. In this case, it is, oh, I see. It is log. Sorry if it's making you feeling dizzy. Go good. And you need to know properties of logs. That is important. To be honest, like it went to the most important, one of the top 10, top 13 important formulas in the world, and one of them is log. So specifically properties of log. It changed science forever, and it's just so simple and it's elegant. So don't confuse it with some kind of stupid algebra. It's actually pretty fundamental stuff to use. It's very applied. It's not even part of the pure math anymore. It's everywhere. Logs are everywhere. So let me put it in red, pink, ln x plus, let me think how to show it. No, it's fine. ln y, I would do the other way around, right? ln looks at the product and breaks it into sum because logarithmic function slows everything down. Product is fast. It's also, when you code it in computer, it takes space. So it's very handy, and usually people use a lot to slow down the process by using log. ln looks at the quotient and makes a difference out of it. Finally, ln looks at the power and makes product out of it. So let me put it like this. And goes down. By going down, I mean it is multiplied now. And you can always put it back if you want. So those three are the most important things. And they used to be everywhere in computer science when they were lack of space in the memory, when the 8 megabyte flash drive costed $100. That's when we were coding in schools with restriction of memory. So I was learning coding, and I was coding computer games and stuff as a homework. And the most important rule was you cannot go overboard over the memory size of, say, memory size. So these things helped a lot. That's why they used to be used a lot. Now they're used in different places too, different applications. So what you do first, you use this property. It's going to be, so it's not ln over ln. I also tell my students this week, log works with inputs, but there's no formula that tells you what to do with log over log or log times log. There's no formula for that. It doesn't work with output. It helps you with inputs, like so. So it's going to be ln, and inputs are now combined into the ratio 5 plus 3x, 5 plus 2x. I just remember whatever has negative sign goes to the bottom, like so. Now there's a property for the limits that we learned at the very beginning, that for the good functions, when limits exist, you can put limit inside. So it's going to be ln. And now this takes you to the very first topic, and we just reviewed it actually. Limits to infinity. 5 plus 3x, 5 plus 2x, like so. Find the leader, find the leader. They win. If the speed is the same, it will be the ratio of the leading coefficient. So the answer is 3 over 2, almost, because it was inside of the log. So ln of 3 over 2, which is actually ln 3 minus ln 2, but that doesn't matter. So this is how you can work with these cool little problems. They're kind of like, if you know how to do them, they're very easy. Technically speaking, you just stare this little bit and you know the answer. But if you don't know, then it's hard. So it's 3x over 2x because of this negative sign and because it's at infinity. That's 3 halves, done. But inside of the log. So kind of, if you know it, it's a very good problem. But if you don't, then it's not a good problem. Now, I wanted to show some derivatives, of course. Do I have this on my list? Yeah, 32 and 34. What was 32? Oh, yeah, these guys. Let's copy these derivatives. 32. Oh, let's not do second derivative. Let's just do first one. Second one, you just, well, maybe let's do, I don't know, let's see how hard it is. I would like to move on to integral since it's a recent topic. So, f prime is, okay, you need to remember, maybe this is the good time to finally build a table of derivatives. Now, we require you to know everything. So let's see what we learned in general again. Derivatives. And I'm not talking about chain rule and stuff. I'm talking about formulas which are no other way but just to memorize. First, we had TRIGS. Red. Sine x prime cosine x prime equals. Sine is a normal guy, gives you cosine. Cosine is a weirdo, gives you minus sign. That's how you can try to remember. Cosine is weirder in many ways, to be honest, and it will be more weirder in upper level. Then we gave you tangent. Tangent x, and in America, secant x. Secant and cosecant only exist in American culture, and then because of them, it was spread around the world because of the articles and publications. But none of us Europeans and Asians actually don't learn secant and cosecant. We just call them 1 over sine and 1 over cos. So I wouldn't see a problem with that. So tangent likes secant, and that's why it's secant squared. But secant likes itself, so it copies itself first, and then it says, fine, I'm also a friend with tangent. That's okay. It's silly, but it works. Those are your basic tricks. Now, how about not basic tricks? Those are inverse tricks. Let me put in different color, pink. So arcsine, arccosine, arcsine, arcsecant, arctangent. Arcsine x. Do you know that arcsine and sine minus 1 is the same thing, right? So remember, it is not 1 over sine. Minus 1 on top of the function, on top of the name of the function. It was reserved for the inverse functions. Just remember that. If people want to write down my 1 over sine, they have to write down 1 over sine, or they put parentheses and they put minus 1 outside. Then it's going to be 1 over. So around the world, people somehow decided on that, which is very nice. So derivative of arcsine, 1 over. Derivative of arcsecant, 1 over. And derivative of arctangent x, 1 over. Which one is which? The easiest one to remember is tangent. Tangent is the only one that has no square root, and it has 1 plus x squared. Done. That's it. Now the other one have a square root. So let me put square root, and square root. And the other one has input squared minus 1. And the other one has 1 minus input squared. Which one is which? That's the hard one to remember. So I just once memorized, and I was good at that. Basically, remember that arcsine starts with 1. But I don't know, if you have any fun way to remember why, let me know. Starts with 1. 1 minus input squared. And then arcsecant is the other way. X squared minus 1. So this, here you go. Here are your formulas. You need to know them. Unfortunately, it's important. 1 over. Put this in the box. And chain rule is involved all the time. That means, let's go to chain rule later. Finally, the last two. The last two are e to the x prime gives you e to the x. ln x prime gives you 1 over x. They are also formula with a, and I just did not put them on a test. And it's nice to know what a to the x is. A to the x prime, still copy, but times ln of the base. And it's nice to know that log base a is 1 over x, just like before, but also over ln of the base. I don't know, for the test, and in general, everyone using those two. And also log base 10, basically. People know log base 10. So, knowing these 3 massive tables, you are skilled to do everything in this life. Let me show you change over a little bit. E to the u prime is copy times u prime. That's when u is a function. For example, e to the 5x squared prime is e to the 5x squared times derivative of the function inside. But inside, in this case, it's in the exponent. like so. So times 10x. So that's the example. Okay. With the log, it goes the same way. So that's why I'm going to show log here. Log has stuff inside. Just don't see it for a second. See it as the log of u. And you know how to deal with the log of u. Write down minus 16. Open parentheses. Derivative of log is 1 over stuff inside. Okay? So just follow this idea. Whatever the stuff inside, it will be forced to go down. Going down to the denominator. But then, like, why would you put u if you know it's constant x? But just put it back. So, okay, you just copy the function, but in the denominator. Then Chino says times. Now you can look inside and you see it's constant and you differentiate. And that is the answer. And I don't want to, oh, actually, I know how they did the secant thing. The sine over cosine is tangent and derivative of tangent is secant squared. Whatever, not very interesting to be honest. So know that. Let me check the chat. Then, yeah, this guy, arcsecant. Be confident if you see arcsecant. Let me just write it down. Arcsecant, no, like arcsine 6 to x plus 4. Arcsine, sine to the 6 to x plus 4. Y equals. Be confident when you see arcsine or sine minus 1. That is the same thing. Remember that. Arcsine and sine minus 1. That is number 3. Y prime equals. You need to first figure out which function is outside. Well, the outside function is the one that you will use last if we ask you to plug a number. Say if you plug x equals 1, this will be the first step. 2 times 1 plus 4. The next step will be arcsine of that result, and the last step will be 6. So 6 is the last function. So you do it first. 6 goes down, everything to the 5. That's how you see it. Another way is to rewrite it. As arcsine of 2x plus 4 and everything to the 6. That's the other way to see it. Then you definitely visually see that 6 is the outside function. 6 goes down, copy everything you see because that's your u, right? That is your u. Arc sine of 2x plus 4, like so, times the derivative of the function inside. Well, now I see that it's arcsine, and arcsine has u inside, so I treat it as arcsine of u. And I know the derivative of arcsine. It's 1 over a square root. Input squared minus 1 or 1 minus input squared. And I told you sine. Maybe because like it's I looks like 1, so 1 minus, I don't know, to be honest. I just memorized. That's like a rare case. I did not figure out any way to memorize it better. So 1 minus input squared. That's u squared. So what is going to be inside of u? Instead of u, 2x plus 4 squared. That's how it works. So remember, it's input squared. That's why sometimes I like to give these formulas using u instead of x. So people remember, no matter what it is, no matter how crazy this thing inside, you're gonna put it in the denominator and you're going to square it. And then times u prime, times u prime, times u prime. That is the idea. So that's what I'm gonna do right now. I will do times u prime. U is 2x plus 4. That's 2. That is the answer. Carefully type it in. That's gonna be a headache to type. But that's why I'm helping you and I just check later what is going on. The people doing fine, but very quiet. Kind of.
Thanks for that one. I always miss it where there's 2 chain rules.
Yeah, 2 chain rules are the worst. That's why. No wonder, because it's hard. So let's move on. I was like, what if you cannot hear me? You know, there was a professor who was like teaching something for 2 hours and then he was muted. And people were not able to tell him because he did not check the chat. So that was, I can imagine how sad it was. Now, L'Hopital rule. L'Hopital rule should be your favorite topic ever. Don't be scared about that. Let me show you why. Let me show you this example. L'Hopital rule is amazing. It's actually very cool, and in general, people stick to it in future classes too when they know how to use it. So did I identify what's happening? Okay, derivatives. That's what derivatives. Now, we covered all the derivatives. If you think about it, we covered log, e, sine, cosine, tangent, secant. Well, more or less. Secant gonna show up in integration again. I will show you. Arcsine, arcsecant, arctangent. Don't need to know any other derivatives. Just letting you know. Arcsecant or cotangent. Who cares? To be honest, can just I would rewrite them as the functions I know. There's limited space in the brain to remember everything. So L'Hopital's rule. People do not agree how to write his name. Sometimes it's a hospital. Sometimes there's no S. So it's kind of funny actually how you see it. Lots of memes about hospital and stuff. But I like to put it in the circle. That's how I was taught. In my language, we just do L'Hopital with no H. So we put L in the circle, but I switched to the director to L and H in the circle. That means L'Hopital. You put the sign, everyone know more or less that that's L'Hopital rule. L'Hopital rule only works when you have 0 over 0 case or infinity over an infinity case. That's it. You cannot use it all the time. But if you can use it, you take derivative of the function top and the function the bottom separately. And apparently when it's a limit, it doesn't matter. So it will be equal to the original. X approaches A, F over G. So if it's easier to work with derivatives, you do that. That's basically linear approximation for you. Instead of working with the original function, we're using its derivative because it's a tangent line, blah, blah, blah. We're approximating it linearly and then finding the limit. Because limit is not exact, well, limit is limiting position. So why not to play with that when you can? 6 to the x and 8 to the x. At 0 is 1 and minus 1. It gives you 0 dividing by 0. Boom, you can use L'Hopital rule. So I do this notation for myself not to forget, because to be honest, it looks very unusual why this equals the derivatives suddenly. It's hard to, later when you look at it, it's hard to remember what did you do. So when I put some note, and I like to put a note, L in circle, it means I did L'Hopital rule. So derivative of 6 to the x is you copy times natural log of the base minus derivative a to the x. You copy times natural log of the base over 1. Well, the moment you got 1, you win. That's it. Whatever the answer now is going to be, that's the answer. You don't have to be bothered by this anymore. Well, 6 to the 0 is 1, 8 to the 0 is 1. It's ln 6 minus ln 8, which actually can be written as ln 6 over 8. ln 6 over 8, which is 3 over 4. Well, it doesn't matter. Just type it in and whatever you want, and you're done. So those questions are good. Or one more example. Limit as x approaches infinity. I wanted to have 2 examples. 0 infinity. X to the 11 plus 3. 7x to the 20 minus 4. Excellent. You check first if you can use L'Hopital rule. And then 3 quarters. You check first, and indeed it is infinity over infinity case. X to the 11 and x to the 20 blow up to infinity. Everything follows, blah, blah, blah. It's infinity over infinity. Let's use L'Hopital. L'Hopital rule says, don't worry, just differentiate the top and the bottom as many times as you want. If you keep having infinity, just keep going. 11 x to the 10, 7 times 20, 140, x to the 19. And you're already done because now you just simplify a little bit. Don't oversimplify. It's not 11 over 14, okay? You just use now my logic. Well, you actually don't have, probably weird to say 140. The denominator wins at infinity. So you're dividing by the biggest numbers you know, it gives you the smallest number you know. Or you actually simplify 11 over 140 times x in the denominator at 9. Well, at infinity, that gives you 0. So both ways are fine. So those are supposed to be your favorite problems. Just don't freak out. Good. Keep going. Let me know what you feel about that. If you have any comments, critics, suggestions. See, we already did exam review 3. I wonder if I should have started with the recent topic, so you feel good about that. But I'm happy to stay as long as needed until my tablet dies, I guess. Something else here? No. Okay, and of course, it's maximum minimum stuff. That will take forever to review, so that one you might need to watch exam 3 review, which was really good, I think. But what I put in my note was, what is this? Maximum, what is that? Oh, the logarithms. Oh, master exam. There's in my note to practice with you some master exam stuff. Oh, I can do it later. I guess I can do it now. Since we're already leaving differentiation. Now we're going to applications of derivatives and then integrals right after that. But in my notes, I wanted to show one last time. What is derivative of these functions? Ln of x to the 6 plus 2x, e to the x to the 6 plus 2x. Cosine of x to the 6 plus 2x. And secant of x to the 6 plus 2x. That's what I put it in my notes to try to explain. When you compare, I think it's much better in general. Well, let's do it. It's kind of like practice. Practice all possible derivatives. So, derivatives. Y prime is, so 1, 2, 3, 4. For number 1, you do 1 over everything you see inside of log. So don't be bothered by it, just copy it there. And then you do times the derivative of the function inside. So what many people like to do, and what I like to do, is to put them right on the top, 6x to the 5 plus 2. It's kind of safe space and easier to type, because then if you type it, you put parentheses, slash parentheses, right? So I like it this way more, versus 1 over parentheses in blah, blah, blah. So times the derivative of the function inside. You look at this, stare a little bit at it, and multiply by 6x to the 5 plus 2. Y prime for exponential function is you copy until we go to the multivariable derivatives. It's always copy. Finally, in calculus 3, we're going to find out that some derivatives of e to the x is actually 0. Finally, we're going to get into that. But that's going to be in calculus 3. It's because you can differentiate with respect to another variable. With respect to another variable, it's a constant, so it's 0. That's going to be a pretty cool idea in general. But until now, how fast exponential function is? It's as fast as itself times the derivative of the function inside. But by the function inside, we mean in the exponent. Well, still inside. It actually makes sense if you type it in, because it's exp at x to the 6 plus 2x. If you type it in the code, this is how it looks. So it's literally inside of it when you type it in as the code. Yeah, anyway, you got it. Now, cosine is the same thing, but your job is to remember about the negative sign, right? Yeah. cosine y prime equals minus sine, copy the stuff inside, times the derivative of the stuff inside. And my favorite I wanted to show you is secant. I deeply dislike secant functions. And this is why. Like, try to explain to Calculus 1 students. They just learn the stuff and it's fresh, it's new. And then look at this. Not only it copies itself, right? But then it has tangent, right? And then times the derivative of the function inside. That's how tricky it is. So the first part is just because of the formula of the secant prime. Has nothing to do to chain rule yet. That's how weird it is. And then that is chain rule. So that's what I think is challenging. So you copy it first. It's going to be x, secant likes itself. So secant x to the 6 plus 2x. Then it remembers about tangent and says, fine, it's going to be tangent x to the 6 plus 2x. And that's just the formula. And then times the derivative of the function inside. And that is 6x, the 5 plus 2. Here's your comparison, basically. That's, I thought was handy to explain. Now, there's something. I think we just reviewed all of this on Tuesday. So I'm going to go to integrals right now. And then if we want, we can go back and review this stuff again. Can you imagine it was on Tuesday? It feels like kind of long ago, but it was already recent. So let's do the recent stuff, which is 5.3 and 5.4, which is due tonight. So bad, there is no space to move anymore. This stuff. But these ones are possible to finish fast. Although it's not simple. It's just kind of, it goes fast if you can, I guess better to say. It goes fast if you know how to do it, which is better. 5.3, I have some notes, number 6, 2, and 4. Okay. Number 2, number 4. Oh, those two practice. Let's practice to practice the definite integral. So, number 2 and number 4. Good. So we're going to chapter 5. We're going to chapter 5.3. Chapter 5.3 and 5.4 are about integration. Finally, this antiderivative we keep talking was connected to integration. Integration is the whole process of undoing differentiation. And also they connected it to areas. It has lots of application. Double integral gives you volume of stuff. So like volume of the vase you're looking at. Triple integral will give you hypervolume, which is volume of the 4-dimensional object. And not only that, it's very interesting how in calculus 3 we're going to do these things. You are a 3-dimensional object, and you have a 2-dimensional shadow on the floor. So that is that's called a projection. What is the area of the 2-dimensional shadow? That's 1 dimension less than what you are. So it's very interesting that there is a 4-dimensional being that have you as a shadow, and you are a 3-dimensional being. So what is the volume of that 4-dimensional being? That's like we're gonna be doing that. And it has lots of applications because increasing dimensions not necessarily mean increasing it to the crazy ideas and fascinating ideas of upper dimension. But also when you're talking about your lungs, right? We can find the volume of the lungs in your body. But also there's a special pressure happening in your lungs. So double integral gives you volume of the lungs. But one more dimension will give you also with respect to air pressure in the lungs. And it's not the same as everywhere in the body. Even temperature in the lungs is higher, blah, blah, blah. So that's what the 4th dimension is often. It's another property of your body. You have a 3-dimensional body, and the 4-dimensional can be a temperature around your body, for example. What's the temperature? For you to know, temperature in your armpit is not the same as temperature in your lungs, for example, or heart, or in other places where the thermometer can be sticked into. So let's do that. Oh, let me write down the formula first. Integral from a to b, f of x dx. The capital F of x is that thing we have, small f. The small f is the derivative of the original function. And now we're integrating, we're undoing differentiation. So it's going to be antiderivative plug top minus antiderivative plug at the bottom. That's called fundamental theorem of calculus, FTC. And it was like part 1, part 2, blah, blah, blah. So this is a fascinating result that was made in the world. Yeah, let me know if there's a problem with sounds and stuff. So this was the most important achievement in previous centuries. It's literally changed everything. Such an elegant connection, and the connection was given between antiderivatives and areas, basically. Well, it's not just areas, but like accumulate. It's called accumulation, accumulating function. So this equal sign is what's supposed to give author or Nobel Prize and stuff, but there's no Nobel Prize in math, but it's fine. So my point is that's what deserves it. Like if you wonder what Nobel Prize looks like, this small elegant equation deserves it. And sometimes small elegant things are the most brilliant one, like the gravitational formula, blah, blah, blah. So let's practice on that. Integral from 3 to square root of 15 of 10 over 1 plus x squared dx. Well, this is already horrible, right? You look at this and you kind of freak out. Well, maybe you will recognize something you know. Step 1, I highly recommend you to kick out the constant if you can. Constant is multiplied by this fraction. That means I have right to kick it out. May kick it out, it means I will write it down as a product outside of the integral dx. You can bring it back if you want, but it's times 10, so the result will be this integral times 10, so it's the same thing as the original. And now your brain should stare at this, just like ignore the integral sign, it scares you. Look at this and ask yourself, derivative of what function gave you that? And that's how you ask yourself, derivative of what function, right, gave you that? And you're like, wait, isn't it arctangent? And it is arctangent. Arctangent. And since there is no stuff happening with x, it's just arctangent x. We're going to learn later what to do if it's 2x or x cubed over 5. That's going to be the first chapter of calculus 2 class called literally actually the first chapter, 5.5. Now, this is the notation. This is international notation. You put a bar and you put 3 and square root of 15 at that bar. Isn't it interesting that people in India, China, France, and even in Canada, that's my favorite joke, do exactly the same notation? Before the internet, people somehow agreed on that. Isn't it crazy? Sometimes I just feel it's crazy. So the formula says 10, or either you open these parentheses or you open these parentheses. Both are correct. And now you plug the top function into this minus the bottom, not the function number. Top number minus the bottom number into the function. It will be 10 arctan. That's fine. You can write down tangent minus 1 if you want. But when you copy it to the web work, I don't recommend you to do minus 1 because you know how much it doesn't like parentheses and stuff. Arctan is easy to type and write. Minus 10 arctan of 3. That is the answer. And either you put 10 outside or not. And that's it. Don't try to find it. In the answer in WebWork, I see they give you some kind of number. Like, why? Why would you do that? Just type it in as it is and you're good to go. So that is notation. That is how people are doing it. 10 minus 1. Yes, you can do that too. You can write down or 10 arc. No, why did I say that? 10 minus 1 of square root of 15 minus 10 minus 1 of 3. Sure, that's the same thing. no difference. Then I don't even need those parentheses. Both are correct. And actually, people don't have preferences. Around the world, there is no preference, to be honest. Now, do you have questions about that? That's like a new material. And it a little bit covers your recent homework, so it's nice. I'm glad that we can talk about it. Number 4. It's kind of like secant, so I'm not sure. Let's do number 5. So of course, you should know all these, right? Let's do all of this actually. Why not? Copy. Let's do all of this. And again, stop me if you want to talk about this. If you want to talk about this. It's like a therapy session. Feel free to talk about this. You stare at the function inside and you try to recognize what gave you this derivative. Yeah, derivative of what gave you this, basically. Constants freak out students at first, then they get used to them. That's why I highly recommend just to kick them out. If it's multiplied by a constant, why not to kick it out? This one have to be factored out to be kicked out. But maybe that one actually does not hurt you. So before integrating, I'm going to repeat the integral sign. Also, you know, practice right away to have a beautiful integral sign. Because it's not in person class, I cannot force you to do it, but I highly recommend you to do it. Integral sign is not S, it's not a line, and it's not a weird, ugly stuff I see in my test. And beautifully, it actually looks like this. Sometimes people do even nice, like curly thingy, but basically it's that. It's a little bit stretched S, so don't be weird right away. It's going to be hard to get used to good notation later. It's going to be 1 over square root 1 minus x squared dx. Now you stare at the function inside and you ask yourself, derivative of what gave you 1 over square root? And then you remember that I said, oh, 1 over square root, 1 minus stuff, that's derivative of arc sine or arc secant. It depends on the situation. So I'm going to put 2. And I'll remember that if it starts with 1, that's arc sine. Arc sine of x. Notation is bar, so integral sign disappears when you integrated the function. Not only integral sign disappears, but integral and dx disappears when you integrated the integral. The idea is that this is the input of the integral called integrand. The beginning of the integral is identified by the nice, beautiful integral sign, and the end is identified with d stuff, so d variable, dx, dt, dm. It's not correct to write it without integral and then 5x equals. No, where is your dx? Dx literally tells you when integral stops. That is why if I write down integral 5x plus 3, where is the end of the integral? It's here if dx is at the end, or it's here if dx is before plus. So that's why it's important. It identifies the end. And also the way it was derived and everything, the formula actually involves differentials. And dx is one of that stuff. 0, square root of 3 over 2. Plug the top minus the bottom. You can write down, you can start right now typing the answer actually. You will type in 2, because it was right in front of it all the time, right? 2. Arc sine, or sine minus 1, of top goes first, square root of 3 over 2, minus 2, arc sine of 0. Type this in, you're fine. This is a good answer. If you're not stressing too much, you can remember that arc sine of 0 is 0, and then sine of what angle gives you square root of 3 over 3. If you're afraid to mess up, then just don't. Just type everything in, and the answer will be accepted, because they're checking your integration skills, so it's fine. Let's do these guys. Well, that kind of requires more formulas, right? So derivative of what gave you 1 over x? It's log, but unfortunately, the absolute value is involved, which means you need to know that integral of e to the x dx gives you e to the x plus c. plus c because it's antiderivatives. If you have definite integral, plus c disappears. Do you know why? First of all, the answer should be exact number. Oh, over here. Integration. Definite integral gives you a number. So it's a value of 5 kilometers or so on. While indefinite integral gives you a function. So it's x squared plus 5 and plus c. It's a family of functions. Remember that there should be no c when you work with definite integrals. In general, if you look at the formula, capital F is antiderivative plus c minus capital F plus c, but that's parentheses. C minus c gives you 0. So even if you put c for each case, it gets canceled out. In the example of arctangent, it will be arctangent plus c and arctangent plus c. But because of the parentheses, c minus c gives you 0. So basically don't be bothered. Use plus c if you see a definite thing. Kick the 2 out. 2 integral 1 over x dx from 1 to the e to the 5. While e to the x is e to the x, 1 over x dx, you ask yourself, what gave you 1 over x when you differentiated it? And you're like, oh, log gave me that. But there is a problem. X in this integral can be negative. It cannot be 0, but it can be minus 5, for example. While x in the log cannot be negative. To make sure we don't have ln of minus 5, we put absolute value. Now, even if x is minus 5, someone gave you, say, what happens with minus 5? It will be ln of absolute value of minus 5, which exists because it's ln of 5. So absolute value fixes the domain. That is the idea. Or just remember it's absolute value. That's also one of the things. And remember that integral of x to the n dx is x to the n plus 1 over n plus 1. You only calculate it once, and then you copy it and you divide it by that number, so you don't have to calculate it twice. That's called power rule. So there's 3 new formulas to remember. Maybe even 2 because e to the x is just e to the x. So equals 2. You stare the part inside and you force yourself to remember what gave you that 1 over x after differentiation. Natural log of absolute value x gave you that. Since it was a definite integral, you put bar 1 e to the 5. Plug the top minus the bottom. Maybe I like to write it down. In the future, we'll have more stuff with the top minus the bottom. There will be a top you can calculate too. Area between graphs. And it's also it will involve top graph minus the bottom graph. And then it gives you area between both. So I like mentioning that top minus the bottom. Minus is important. Make sure it's difference. We're taking the difference. So 2 ln absolute value of e to the 5. E to the 5 is not negative number, so you could drop absolute value. Minus 2 ln of 1. Same thing. Okay, same thing as before. If you hesitant because you're freaking out, type this in. This is the correct answer. But you could simplify. ln undoes e because they're inverse functions to each other. ln of e is 1. Raised to the 5, then it's just 5. Remember that 5 goes down when it comes to ln. So it's going to be 2 times 5 minus 0. Because ln of 1 is 0. E to what power gives you 1? 0. So the answer is 10. So that will be easy to type. But if you don't trust yourself, which is fine too, then type everything in. It will be accepted. Finally, how to work with several. How to work with several pieces in the integral. You work with them, imagining there are many integrals right away. So what happens with 4e to the x when you're integrating it? It will be 4e to the x. Does that make sense? Because 4 goes up, and it becomes integral of e to the x. Integral of e to the x is e to the x. But at some point, you just stop kicking things out. You just now know integral of 4e to the x is 4e to the x. And then plus, what is integral of 4 sine? Yeah, that's the cool, interesting one. You definitely know that sine and cosine, they interchange. Interchange or exchange? Interchange, I think. So sine gives you cosine, cosine gives you sine when you differentiate and integrate. Your job now to know if it's plus or minus. So what I recommend to do is you write down first that it's cosine. And then you ask yourself, the derivative of cosine is minus sine. Oh, so I have to put minus. That's the idea. More you memorize it. But to be honest, the less you memorize, the better it is. That's my point of view. Integral of sine x dx is minus cosine x plus c. While integral of cosine x dx is plus sine x plus c. So derivative of sine is positive cosine. That's why it's plus. While derivative of cosine is minus sine. So you put minus. That's how you do. I just memorize derivatives only. And I know it when doing the process. Bar 1 and e. People don't even put parentheses, to be honest. But if you can, if you want, you can put parentheses. And now you plug everywhere e first, and then you plug everywhere 1 and put minus in between. Equals. Make sure you have parentheses. Many of us forget to use parentheses, and then you make big mistakes. I highly, highly recommend not to forget to use parentheses. That's very important. Parentheses is everything. So it's going to be 4e to the e. That's a number. Don't be bothered with it. It's 2.7, whatever, right? With lots of infinitely many data. That's some kind of number. And minus, that's still inside of the first guy. 4 cosine e. Cosine e is also some kind of number. It's cosine of 2.7, blah, blah, blah. Don't be bothered to calculate that. Minus, and now you plug, so that was top. Now you plug the bottom everywhere. It's going to be 4e to the 1 minus 4 cosine of 1. Cosine of 1 is not 0, by the way. Many people think so. Cosine of 1 is a number. 1 here is a radical radian. It's not 1%. It's 1 radian. So just write it down as it is. Just don't complicate anything. Just type this weird answer and get full credit. That makes sense. Let me check. Very good. What do you think about that? So I added more formulas. Power rule, that's the most important one. E and log. And the not a new stuff is sine and cosine. That's not new, to be honest. So I think so. Let me see. What do you think about this? Now, so I did 5, 2, 4. I did 2, 4, 5. I did all 3. Okay. Then it says number 9. So practice these, guys. These are not hard if you know that you need to simplify them first. Nobody requires you to do quotient rule with the integration. Yeah, in calculus too, we're going to do quotient rule with integration. But they want you to simplify x to 4 over x squared minus 8x squared over x squared, and so on. And then cancel out lots of stuff, blah, blah, blah. And then you have lots of power rule. Same here. This is integral of x, 1/2 plus 1, that's 3/2, plus 2 squared of x. And then you integrate that. So it's the same stuff, just looks weird. They're trying to trick you. That's like literally what I'm trying to tell you. That is actually me. Like this is a trick. They're trying to like trick your brain that you don't know how to do that, which is not nice, in my opinion. And so finally, the very last topic, I think so. That's the fundamental theorem of calculus part 1. Sometimes it's called part 2, but actually or sometimes called part 2, that's called part 1. I wrote down number 9. Why? What's here? Oh, that's probably a different review number. Oh, well, I need to find it. 5.4. 5.4, number 6. Oh, there was this one, number 9. Okay, let's do this one. It's in my notes, so I guess let's show. Okay. Number 9, and we're almost done. Check it out. But we can go back to the next main stuff. How to integrate the stuff like this. That's algebra, your favorite part. If you are bad at algebra, which many of us are, don't be upset. People taking calculus 3 class and they can calculate triple integrals with dx, dy, dz, and we have actually more than triple, we have more than that. That's 5 dimensions for you. And they still gonna mess up, unfortunately, x to 1/2 times x. It's just a thing, so don't be upset about that. The more you do it, the better you become at it. Your job is to try to be better at this. So you see, I'm not integrating yet. I'm still keeping the integral sign. That means I just want to simplify something. X to 1/2 times x to 1 is x to 3/2, because 1/2 plus 1, plus x to the 1/2 times 2. And you see, you have to put the x, or else it doesn't make sense clearly where is the end of the integral. Here it is. And because of the x, actually, I don't need to put parentheses, because the x tells me where the end. Now, integral sign will go away because I will be integrating x to the 3/2 plus 1 over 3/2 plus 1. That's a power rule I just reviewed. Plus 2x to the 1/2 plus 1 over 1/2 plus 1. They go n plus c. Since it's not a definite integral, you have to put plus c at the end. And now you just calculate it once and divide by the same number. 3/2, 3 over 2 plus 2 over 2 is 5 over 2 divided by 5 over 2 plus 2 times x. 1 over 2 plus 2 over 2 is 3 over 2 divided by 3 over 2 plus c. Well, it is ugly. So normally people remember that you need to multiply by the reciprocal when you divide by a fraction. Reciprocal means flip. 2 over 5x, 5 over 2. That's how it should look. It's like very classical look. 2/5, 5/2. Plus 2 times 2/3 x to the 3/2 plus c. Yes, you can multiply 2 by 2 before, or you can just type it in among 1. Or you can multiply while you're typing it in. But that is the answer. Next is, I wanted to do number 6. Oh, and I also want to do average. Stupid average thing. Here it is. Okay, let's do that. Before we move on to derivative of the integral. So find the average velocity. In general, it's like a whole topic of average function. So apparently, that is one of the applications of the integral, to find the average. I'm actually showing it using COVID graphs when I teach it. When it was the beginning, especially, I like epidemiology in general. I was doing research with CDC in epidemiology, mathematical modeling of epidemic spreads in hospitals and stuff. So it's very interesting that you have those graphs and the data. So it's applications. Well, I'm not going to find it here. It's in calculus 2 class. Well, actually, no, it's not in calculus 2. Here you go, area under the graph. So I show people a cool graph, see, of some kind of epidemic spreads. And you know, COVID was a big deal before, still is, but at least not so annoying anymore. So, oh, there's a question in chat. I will answer in a second. So here's the graph, and it doesn't have anything in it. And how do you know the average of people being sick from this year to this year, you know? Or from beginning to this year, 2020, February 11. So the average apparently is an integral from a to b of this function f of x. And f of x is here. So do you know how people do it? You guys just learn left, middle, point, right, and so on. You see what they're doing? They're actually using those bars. Those bars are number of people, but they also can be used to approximate the area below the graph using midpoints and blah, blah, blah. So what people do is data fit. They're fitting the data. That's statistical method. Like so. Now there's the graph of the function y equals f of x. Here you go. So if you integrate f of x from a to b and say this is b, maybe I don't need all years. Maybe I just need from January till February. This is what it is, for 1 month approximately. That gives me all the area. That will be total number of people getting sick, being sick. And that's how hospitals know if they will have overcrowdedness or not in 1 month. They can predict the future. But what if I know the average? What was the average? The average will be divided by length of the interval. That is the average people being sick, average, per time slot, right? So if it's days per day, if it's month per month, in this case, day. So that makes sense because integral is a fancy sum. It's just a sum. We're summing lots of things. How to find the average of your grade, exam grade, if you have 5 exams? Well, you know how to do it. You take exam 1 grade, add to exam 2, x to exam 3, m to the mastery exam, and the final exam. And you do what? You divide by the length of the interval by 5 exams. And guess what it gives you? Average. Isn't it clever? So we've already been doing that for a while with students. But if you have thousands of values, are you going to be doing it so separately? No, instead you integrate. Integration is the accumulation of data. It's a fancy sum, basically. It's a summation. So if they ask you for the average function, let me write it down. Oh, actually, I just write it down separately. Oh, I have a fancy graph here too. Here it is. Total area is here, average is here. How to find average? Integrate and divide by the length of the intervals. Yes, have that. Go back to the views. Found. Let's write down the formula. Average. If they ask you on the exam to find average, then you integrate a function that they gave you from the on the interval they gave you, and you don't forget to divide by the interval first. So I recommend to do it first because people tend to forget. You get excited that you finish integration and you forgot to average it up. So this means average it up. No, I mean this division means not total. That means average. Divide by the number of exams you took. So I'm reading this, lots of English, blah, 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 and then I see, find the average. Oh, okay, fine. So still velocity. That means I don't need to find acceleration or blah, blah, blah. They want me to find the average of this stuff. That means it will be 1 over 4 minus 2. Write down this first, because I'm telling you, you're going to forget. Students just forget to divide by the length of the interval. And they always give it. Times the integral from 2 to 4. 2t1/2 plus 3 dt. And before I move on, people ask that the web work doesn't ask us to add plus c. Yeah, if it doesn't ask, then don't. Usually in the web work, it says it's like squared plus c. I saw examples when I did not do that. It actually asks you to put plus c. But on the exam, most of them have plus c for you. So that's good. It's upsetting to lose all the points because of that. Integrate 1 over 2 if you simplify. And then you start integrating. 2 times t. 1/2 plus 1 is 3/2. And we already know it's going to be 2 times 2/3 if you want to be fast. What is integral of 3? To figure out what is integral of a number, a, you ask yourself, derivative of what gave you that number? A times t. Or x, let's do x for this, so you have a nice formula. Actually, let's add it to the formulas. It's not a new formula, it's still power rule. It's just integral of a dx is ax plus c. It's just x is here hidden with the power 0, and then it becomes 0 plus 1 over 0 plus 1. So it's still part of the power rule. But sometimes it's just confusing. Integral of a is ax plus c. Do you know what naked integral gives you? I like to call it naked integral. Naked integral has 1 in it. So it's actually just x plus c. Because you ask yourself, what gave you 1 after differentiation? X gave you 1 plus it. So you will see that a lot later too. Continue. dt t 3 times t plus c. Because the derivative of 3t is 3. Bar, that's not the answer. Bar 2 and 4. The average velocity should be a number. So they're asking you, so what was the average speed when you were driving? Average speed, that's actually cruise control. So they tell you like average waste, how much on average you use gas when you drive. That's what it is. How do they know that? But also, you know what gives you constant average? Cruise control. Cruise control, if you set it up for 55 miles per hour and then you'll always be driving 50 miles per hour, then it will be the average. So equals 1/2. So keep waiting. Don't multiply by 1/2 yet. Plug the top everywhere you see the variable. Oh, so there is no plus even. If you see definite integral, don't put plus. Plug the bottom everywhere you see. Subtract. So it's going to be 2 times 2 is 4/3. Don't forget to keep all the notation. If there's exponent, keep exponent. If there's a log, keep the log, and so on. Plus 3 times 4. Parentheses is extremely important. Put your parentheses, or else you will mess up. I'm just seeing it way too often, so it bothers me. 4/3 times 2 raised to the 3/2 plus 3 times 2. That is the answer. If you want, let's put huge brackets outside. I like to change between brackets and parentheses so it visually looks good. And colors help. See? So top minus the bottom, let me put it. Top minus the bottom. And you can simplify that. That's actually possible because 4 to the 3/2 is the square root of 4 cubed by the formula of exponent, which is 8 because it's 2 times 2 times 2. Square root of 4 is 8. And this guy, unfortunately, is not. This one is a square root of 2 cubed. So you can first cube, for example, 2 cubed, and then a square root. That is a square root of 8. Which actually can be simplified. Blah, blah, blah. I kind of don't want to do that. So, whatever. 2 times 4. Nobody cares about that. So, in this class, we just want to see that you can integrate for now. Later, it would be a big deal to have better answers. And I think your other classes with physics and engineering will be bothering you with exact answers and simplified answers anyway. So why should I bother you with that? Finally, the last topic to cover is a weird one. If you think that was weird, I personally believe that this topic is weird. The beginning of 5.4. What the heck is that? Why there is a variable in the integral? Oh, and they say differentiate. What is wrong with those people? Well, apparently we need to know how to differentiate integrals. That's going to be a very rare thing. It's important, and that's why I'm going to show it to you. But it's just annoying. And there is a problem like this in the test. That one must be there because it's a whole chapter and it's a big deal in science in general, but you will not be using it for a while. Next time it will show up, it will be like calculus 3 or even later. But you might see it in other classes. That's the one I don't know. Can't claim that. It has lots of applications. It's just like right now at the end of the semester, nobody cares about it. But that's called fundamental theorem calculus part 1, or basically derivative of integral. So can you imagine what is happening here? Integration undoes derivatives, but derivatives undo integral, right? So that means this should be the answer. Cosine t minus e for t plus 1. Because if we're differentiating the integral, don't they just undo each other? And the answer, yeah, they do, actually. So that is correct. The only difference, you need to be careful of how you're doing it. Blah, blah, blah. Actually, those two are not good. Let me check if I have better one. Oh, that's the one. That's the good one. I cannot show all of them, but somehow they start with the hard one first, and then they move on to the easy one. I just don't understand the logic. So let's do the basic one first. Good. So that's going to be example. What is the integral of 1 to x tangent to 11x dx? And they use different variables. For you to know, that's actually not necessary. But they use different variables here. The idea is they ask you to differentiate that. How cool is that? Officially, you saw it in the book. If you saw, well, you probably watched the videos and stuff. In the videos, they do derivative with respect to t, right? So, or x. Oh, I think it's derivative with respect to x, yeah. So you integrated something and now you're differentiating. That means the answer will be this stuff inside because you just undid the process. Now, be careful. Whatever this thing is standing over here at the top, it's important it's at the top, must be at the top. That's what's gonna go inside. And that's it. That's the answer for this example. That's the simplest example. The simplest example, let me show you. I forgot actually to mention that you do have the answers over here. And it's getting harder a little bit, blah, blah, blah. I'm going to show you the harder part. But what did I do with number 3? Oh, I should have done that one. But okay, I can do that one too. It's like, why they differentiated it? No, it was just given. So find the derivative of, you will see it in a test. We just chose some random function and threw it you some random integral. Go. And you do exactly what you did before. No. The problem is, that's why I like this example for now, you will look at it and you're like, oh, Julia told me that 1 over stuff plus stuff is arctangent. No, don't do that. The moment you see a weird x standing somewhere in the integral, that is the last annoying topic. I'm just trying to like give you this memory hint. If you see x in the integral, you don't touch the integral inside. Just don't do it. Don't integrate it. Don't find derivative of cosine or integral of cosine. I'm afraid that will be like a first intention because you just was told to do it 25 times in your homework or more. So you see this x, you know you need to copy the stuff inside. That's the first step at least. Just copy it. Just copy whatever is there. And then I will tell you what to do after that. When you copy it, at least you know you don't have to differentiate or integrate. Because we are undoing integral by differentiating it. Basically kind of canceling it out. Or it's inverting the process, right? Whatever this thing standing on the top, it must be at the top though. If it's at the bottom, that doesn't work. It must be the top. And you just, plug it in. That's it. That is the answer. Boom, we're good. Now there are 2 different cases. Case number 1, what if it has something more than just x? That is chain rule. So of course, chain rule messes up everything. Okay, step 1, look at it. 1, must be at the top. 2, chain rule. Chain rule will do exactly like you did chain rule before. Instead of t, you plug, let me erase it again. You plug 2x everywhere. And then you do 2x times derivative of 2x. That's times 2. That's how you do it. Although, let me see if they want you to factor it. Oh, no. That is problem 1. Yeah, they're factoring it out, so it's fine. Sometimes I saw it times 2 times 2 times 2 because you can do chain rule every single time, right? Cosine 2x times 2 minus e to the 4 times 2x times 2 plus 1 times 2. So I would just do it at the end. The way I just did it. My way is easy to remember. Chain rule. Chain rule says, because you're differentiating, remember that, you're differentiating, right? So there's a chain rule involved. You plug it everywhere without thinking too much about it. Here it is, here's your 8 because 4 times 2x. And then you do times the derivative of the function inside because we're differentiating, chain rule happens, and that's times 2. That's what we're doing here. Another way of seeing it is the integral from 1 to u. You plug u everywhere, just like I told you before. If there's x, you plug x. But because u is a function, you do times u prime. So integral from 1 to u, f of x, right? dx. And you're differentiating that will be f at u times u prime. This is kind of what it means. It's still changing. I did not remember this formula. I just kind of made it up right now. What I remember is a technique. So I recommend you to do that with a technique. Now, I also wanted to show the second scenario. What happens if it is not at the top? But then just flip it. But remember properties of the integral, which says integral from a to b is minus integral from b to a. You're not supposed to write it without dx, but this is like a visual relation. You can flip it by putting a negative sign, so that's fine. That's legal. And why not you do that? That's going to be minus. I'm telling you, like, my idea is, to be honest, first you copy the guy inside right away, so I don't forget it. I don't have to integrate it. Then step 0, right? You write down the inside part because I know we're differentiating it. How do I know it says it? Also because there's an x involved in the integration, in the limit of integration. That's how I know that's the weird one. That Julia says it's weird. You just copy the part inside. Okay, I copy. That's step 0. Step 1, check if the stuff is at the top. Okay, it's not at the top. Put minus. Okay. Step 2, see if you need to use chain rule. Yes, you do. Put x cubed everywhere you see t times 3x squared. Outside. What do you think about that? So that's how you do it. That's my way of explaining. I always explain the fast way. So here is your, do you have a very classical question shows up? What happens with those numbers? Why there's a 3, 1, and nobody asks that? Oh yeah, nobody cares. When you differentiate, it's kind of like when you differentiate, it will be times derivative of 2x and minus or plus derivative of 1. And because derivative of 1 is 0, the other part doesn't make sense. There's another way to explain it, but I don't want to mess up with your brain right now. I just want you to know this technique. The idea is beautiful. It's called a cumulative function, and I can show you a cool animation about it at the end. After this, after the questions and stuff. But just remember, doesn't it? If it's not a variable, doesn't matter what the number is. If it is the variable, then it's not. I did not put 2 variables in the test. But if you have an integral from x squared to x to the 5, for example, a function, let's say cosine x, the x, then you know what to do. There's another property. The property says, if you have an integral from a to b, you can break it to any point c in the middle. So it's going to be from a to c, c to b. Again, you're not supposed to not to write dx, but it's a visualization. And the visualization of this situation is, it was from a to b, and for some reason you needed to break it somewhere to c. It doesn't even have to be in the middle. C is somewhere between. So you find the area from A to C, and then you find the area from C to B, and you add them together, and the total gives you area from A to B. So from area point of view, makes sense. Thus, you do it from x squared to number C. People put 0 usually, but doesn't matter, to be honest, whatever. There are actual ways when you cannot do 0 because it's not in domain. That's, we do not cover this in this class, so don't be bothered. It's cosine x dx plus from C to x to the 5 cosine x dx. Now, as you can see, I was supposed to use t. That's actually not required. That's why I keep forgetting to do that. It doesn't matter. The variable inside of the integral called a dummy variable. That's official terminology. A dummy variable. If you're a computer scientist, you know what it means. It means you can rename it. It's whatever you want. It doesn't matter. It's just used as notation. But it doesn't have any meaning. Look, t time, blah, blah, blah. But I can always rename it to any variable. It just have to be consistent. If it's t inside, then it should be dt. Until we hit calculus 3, then it will be many variables. Equals. And then you do the first integral separately. And just for practice, let me review it again. I told you, if you know they're looking for the derivative, so it's not equals anymore. That's going to be like y. And now they ask you to find y prime. And that's the integral dt prime, right? Then I know I'm going to copy the cosine right away. Step 1, step 0, copy the function because we're differentiating. We're undoing this guy. And that's why it disappears. Maybe that's how I should explain. If you differentiate the integral here, see, it's gone. That's why we copy it. Now, step 2, is the variable thingy on the top? No, minus. We put it in the red. Because then it means I need to flip it. It has to be on the top. It works when it's on the top. It works with the positive sign when it's on the top. And negative sign when it's at the bottom. Then, is it just x or no? No, it's not just x. Okay, so I copy whatever it is times the derivative. That's your first integral. Plus, repeat. Copy whatever is inside. Check. Is the thing at the top or at the bottom? It is at the top, so keep plus. Is it x or x to the stuff or some kind of function? It's function. Copy the function times 5x to 4. That is the answer. Can you do that? Well, I did not put the hard integral like that. I just give you one of these guys. So this is the last topic. That's fundamental theorem of calculus part 1. And to be honest, you will not see it for a while. That's step setting part. You will not see it for a while after that. So I can show you a cool application on that. And you type the questions you have. And accumulative function integral. There's a cool animation on that. I usually show it in class. Image, cumulative. Fine, right? I always think it's accumulation, so it's accumulative. It looks like, well, these I already showed you. And, oh, maybe this one. Let's see. It's going to work. Yeah, post your questions while I'm trying to find a thingy I want to show. Because idea is actually pretty cool about integral from number to x. How it accumulates the area. So basically one of the limits of integration becomes an unknown variable. Or function. Oh. Part 1, x. Maybe that will help. Oh, I should do accumulative area. Oh, that's good. That's usually helpful. I think it's that one, but it's not one. Statistics. There's lots of applications, of course. Here, fundamental theorem of calculus. I think it's this one. No, that's areas. The more areas we have, the better it is. We all know that. Okay. Put it down. I can't find it so fast. It may be in my notes because I'm very my notes of this very good. Fundamental theorem of calculus, part 1. Yeah. Oh, you see, it is here. Hopefully, it still exists. Yay! See, my notes are so organized. I have very good notes. Instead of just finding the integral at the specific place, so here it is. Let's find integral from A to B. Integral from A to B equals number 27.3. That's this area. I just made it up, right? Just this area. But what if I want to keep exploring? What if I want to have next time till this point? That's called D. Let's see it. And then I want to like this point. It's called D. And at some point, I just don't want to decide. I want to have them all. That means I'm not fixing the right point anymore. The left point is fixed, and the right point will be a variable. And x is a runner. It runs to left and to right. You can decrease x and you can increase x. If you decrease, the area will go back to smaller or whatever it is. If you increase, the area will keep accumulating. That's why it's called accumulation or cumulative function. Cumulative area. So you see, x's keep running. The more x is running, the more area is accumulated. And it creates a function. Instead of the number, now we have a function that depends on my choice of the right end point. And apparently, over here, area is increasing, and that's why the function is increasing. Then it hits 0, so that's why it's over here. Max, this is max. And then area becomes negative, so area above the x-axis is positive, below is negative. So at some point it hits 0 because this area cancels out with this area. So the more I go, the more I decrease and hit 0 again. Start with my red function. Start with 0, end it with 0, and so on. I find it pretty cool because it's a very applied engineering idea that I don't want to fix the right end point yet. I want to have it moving to see maybe later where I want to stop. Maybe I want to stop where area is maximized, and now I know it's over here at pi. Or maybe I want to stop when I hit some specific moment. So, whatever. That's kind of the idea. That's how I teach it in class. It's fundamental theorem of calculus, part 1. Area function, blah, 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 and it accumulates. So we trapezoid, how fast area is changing. That's derivative of the integral, right? So how fast, actually, this is a good one. How fast this area is changing. That's derivative of the integral. And this graph is derivative of the integral, the red graph. G is derivative of f, of integral of f, actually. Oh, I think I finally explained it well. Yeah, I think I got. I think I figured out how to explain. So, blah, blah. And the part 2 is the one I just showed. Part 2 is the best. That's the one that everyone wants. Well, that's it. What do you think about all of this review? I showed you lots of stuff. Let me go over those files. And then maybe you tell me what you think we should still cover. This is the last points. You still have 4 hours to work on the homework. So 5.3, 5.4. We covered basic integrals, and I'm not saying they're easy. So unfortunately, you know, it's the problem. We threw such an important topic at the very end of the semester every time, and students just too tired to get it right fast. They're getting it right in calculus 2. I promise you, you will be so good at this that you will be just impressed by yourself every day. How would you become integration? But unfortunately, because it's so fast, the very end, there's just no time to actually get used to it fast. So that's what people who take this class second time, they do much better usually. We did all of these integrals, logs, x, sine, cosine, right? And then we figure out what to do when there's x in top and the bottom. That means they want you to just copy the inside piece and carefully figure out what to plug inside. That means we're differentiating the integral. Plug inside the thingy, change the sign if needed, if it's at the bottom, and multiply by the derivative of that thingy. Average. Average means what? Integral of the function But then don't forget to divide by the length of the interval. I usually do it right away, or else I'll forget to. 1 over pi minus 0 in this case. And it's going to be integral from 0 to pi for this problem number 5. And we did velocity from 2 to 4, integral of this function v, and also 1 over 4 minus 2. That is last chapter. Then master exam, I actually took some functions from here to show you, make sure you can differentiate all this stuff. I know it sounds scary, but I made review with step-by-step solution for every example from this review. That took me weeks of work, and now students from different schools even using those videos to practice differentiation. They really like it. Your job is to be very good in implicit differentiation. We usually put it on the final exam. Again, you just did it in exam 3. You did it in exam 2 and math 3. Do you want me to repeat? Oh, I think I did, right? Yeah, I did integral. I already did implicit differentiation this review. So practice that. Product rule, quotient rule with those things. X to the 5, e to the 2x. Kind of like this example. It's a nice review of lots of stuff. Y equals e to the 5x times x to the 17. Y prime will be, it's a product rule. Derivative of e to the 5x is e to the 5x times 5, because derivative of the function in the top. A function inside, which is in the exponent. Copy x to 17 plus copy e to the 5x times 17 goes down, x to 60. That's the end. I like this one. It's pretty good. Continue. Log 1 over everything times derivative of that everything. I like this one too. I usually show it in my class when we do exponentials, not to be confused between 3 different things. What is, so if y, so it's 1, simple. If y is x to the 15 plus 15 to the x plus 15. Can you find derivative? Do you see the difference? Polynomial has the shape of the input to the number. That's the shape of the polynomial. That means it requires power rule, called power rule. While exponential function has the shape of a number, a fixed constant to the input, to the variable. So input to the variable versus what? No. Variable to the constant versus constant to the variable. That's the difference. So when base is not x, that somehow is hard. And you have to use exponential derivative. Yeah. So it's going to be 15x to the 14 plus exponential says copy times, if base is not e, it's going to be ln of the base. And then it's just 15, derivative of 15 and 15. So that's, I like to show this to see the difference. Oh, and one more, 15x. That's a line, that's a linear function. Gives you 15. How about that? So the difference of all of these 4 cases. Okay, let's see. Secant. Make sure you know how to differentiate and differentiate secant, differentiate tangent, integrate secant squared, blah, blah, blah. It's like, what is the integral of 17 secant x tangent x dx? Do you know? What is that? From 1 to 30. And you look at this and it freaks you out, but you just stare at it a little bit, kick the constant out, and keep staring at the inside part. And ask yourself, derivative of what gave you secant tangent? Oh, it was a secant, derivative of secant. So it's going to be 17 secant x. And you can always check by differentiating it. But then you put bar, instead of plus c, you put bar 1 and 30. And then you plug the top. So it's going to be 7 secant 30, parentheses, minus the bottom, 17 secant 1. That is the answer. So that was a good example. Just like randomly good examples show up in my mind. That is a math exam. Let's check the exam 3. I hope this review was recorded. It would be very upsetting. Yes, it was. So we reviewed on Tuesday. Maybe just rewatch that review because that took also 2 hours. Make sure this is gonna be on the exam. There's no way we don't put that long freaking problem. Unfortunately, it's always like that, where you have to find everything. It's just a problem that asks for everything. You know, you're asking too much basically. But that's the case. Which problem I'm talking about? I'm talking about, let me see if it's here, that has everything. Well, it's not here. But that's the one I did in my review. Well, basically, they broke this into pieces, but I did this one. Which way did it? I did this concavity thing in my review, but I did everything. Increasing, decreasing. Oh, inflection points. See, I think I did this one in my review. I mean, I can do one more if you want, but I do have video specifically for this problem. I call it analyze the function or sketch the graph of the function, where we do everything. I posted my announcement, I remember. We even do symmetry there, which we don't do on this in this class, but still. Find the first derivative, set it equal to 0 in D and E. Find critical points, check that they are in a domain. Throw away the one that's not in a domain. Draw a sign line. Put derivative in the sign line. Check plus minus plus minus. If the derivative is positive, using test point, you check that. Then the original function is increasing. There, negative, then decreasing. Find the second derivative. Set it equal to 0, D and E. Find those points. Throw away the extras. Draw a sign line. Check the sign of the second derivative. That's why it's called second derivative test or second derivative sign line, right? If the second derivative is positive, then the original function is smiling. That's concave up. If it's negative, then the original function is grumpy. That's concave down. So concave up means that there's a cup that can hold some water. Concave down means the cup is upside down and the water will follow. That's kind of what they mean. If they say that the mountain has concave up shape, that means you're going to go down the valley, right? Well, concave down, which is convex, I think, in general use, then it's a mountain that you have to hike up. That's what they mean. Then, if the point changed the concavity from minus to plus or plus to minus, this is what is happening. That point is point of inflection. So it was accumulating water, and it's something changed in the behavior, and now the water is not accumulating anymore, or vice versa. It was going down and going up, like so. It's not increasing, decreasing. It's actually the shape, you know? It's the shape. Because it's decreasing here, which is it's decreasing and increasing. That's a different story. That's your minimum, and that's your maximum. That's first derivative test. Concavity is about the whole picture, where the function is decreasing with decreasing speed and increasing and decreasing with increasing speed, or increasing with decreasing speed and increasing with decreasing speed, blah, blah, blah. And my favorite example is when you are washing your hands with soap, you kill whatever they say, 99 bacteria. But none of us wash hands for whatever it's supposed to be seconds, 20 seconds, because we're too busy and or we don't care, or we just bad people. So you wash your hands and say you killed a lot of bacteria right away, 65%. Will it be better if you wash it second time? Yeah, the answer is yes. If you wash it one more time right after this, you're probably going to kill 99 bacteria. So that's your increasing function. Will it be better if you wash it third time? Maybe, But how many bacteria you're gonna kill? You already killed everything. So it will be still better, but it's not gonna be significantly better. And that's when the speed's dropping, the speed of increasement. What if you wash it 4th time? You barely will see the difference. Does that make sense? And that's what concavity is about. It's somewhere over here. There's a point of inflection when it doesn't make sense to keep washing hands anymore. Once was the best, or the must-have. 2 probably was the best. 3rd one is unnecessary. After 5 times, you're being a weirdo. Or you have mental issues, which is not a funny topic. People actually have people who work in medicine sometimes have a mental issue that they cannot stop watching hands because they've seen stuff and they touch those stuff. So that's like a very good example of concavity. Something is increasing a lot and then slows down the increase. That's concave up. No, that's concave down for you. It's increasing with decreasing speed at some point. Okay, my voice is losing. So let's a little bit speed up so I don't bother you most too much. Let's see. A max mean, also review absolute max mean. I think people do well with those problems, so why not mean value theorem? I mean this one, absolute, where is absolute max mean? Here it is, like number 3. Whatever I showed you last time. People usually do well on those questions, so I kind of like. Review optimization problems. I usually like the fencing problems. They're the best. Everything that takes too much time, I don't put those for test. Now, these ones called initial value problems when you need to find C. We did it last time. That's good too. Particle is moving, jump from acceleration to distance. That's second derivative, second integral actually, anti-derivatives, right? Approximations might be there or might not. The stupid rectangle stuff. Cannot tell you that because sometimes we put, sometimes not. Exam 2. Exam 2 I reviewed really well right now. Let's see. Skip this box. Just annoying box. But definitely check the derivatives. You need to know your derivatives. Derivatives, that's the basic way to check if a person is good in calculus 1. We ask them to find all kind of derivatives, including in the implicit differentiation. So make sure you know how to find a slope, and make sure you need to know how to find the equation of potential. Here's your examples with implicit differentiation. Here are 3 we reviewed those. I don't put linear approximation in the test. People don't do well in these. And I don't put this, what's the name? Differentials. Yeah. We reviewed limits, all kind of limits, with E and without E. And there was L'Hopital rule. Derivative of this number 29, I don't put that either on the test. I already mentioned it. That's the formula of inverse, derivative of inverse. So the inverse function might be there, but derivative of inverse is just hard. People don't do well. If you did your homework, you know what I'm talking about. It's a freaking annoying problem to find the derivative of inverse. Log minus log and log plus log, know what to do with that, if you see that. Logarithmic differentiation, review that. Derivative of arcsine, arcsecant, arctangent, review that, including product rule. Should I do this one? Oh, they have an answer here, so you can practice that. L'Hopital rule with the hospital. Review that, 0 over 0, infinity over infinity. And only one left, exam 1. And exam 1 has limits. I just put limits in the test. No derivative by the definition. Limits and continuity. So make sure you know what to work when we ask you about left limit, right limit, total limit. At an F of stuff. Is it continuous? Is it a jump, infinite discontinuity, or a whole? And review limits algebraically. We will always put at least 1 or 2 problems in a test about that. It's just the thing to do for this class. Wow, that's kind of a lot. I just talked for almost 3 hours. So high respect to those people who are still here. That's pretty impressive, actually, that you're still here. That's very good. I think everything is good. Yes, infinities, here they are. I did that too. Good job, people.
Thank you.
Yeah, good job for coming. That's very good dedication. So the video will be ready probably in 3 hours, which is kind of late. But I will post a note right away. Maybe the notes will. And good luck on the final exam. Let me stop recording. And remember, you're amazing. You can do it.